All right, I think we can get started. So thank you all for joining us. I'm Erin, and also joining me at the printer is Kyle.
Hi, everyone. Hopefully you can see me in front of the printer here. Thanks for joining us, and yeah, look forward to showing you the printer today.
Yeah. So today we'll be talking just about some 3D bioprinting strategies using microfluidic 3D bioprinting. First, talking about how it works, some of the features and benefits it can provide to printing soft tissue constructs, such as the ability to print hollow perfusible tubes and to rapidly switch between materials to print heterogeneous constructs. And then after that, Kyle will take over with a demo of the printer. So Aspect Biosystems is a Canadian company. We're based in the beautiful city of Vancouver. The company started out in a UBC lab with the development of a microfluidic 3D bioprinting technology. And in the last few years, we've grown to over 50 employees. And so here at Aspect, our focus is on creating bioprinted implantable therapeutics. So we have an internal team of researchers working towards this, and we also partner strategically with academic, medical, and industry partners. Now, the field of bioprinting involves using 3D printing methods to precisely organize cells and biomaterials into functional 3D tissue structures. And those can be used for applications such as the development of in vitro tissue models and bioprinted therapeutics. Microfluidic 3D bioprinting adds an additional level of control to this by using microfluidic print heads to combine and organize the cells and biomaterials. So mixtures of cells and biomaterials that are appropriate for bioprinting are known as bioinks. And a 3D structure is defined in the software so that the RX1 bioprinter and microfluidic print heads can print those bioinks into a specific design. The RX1 bioprinter itself has two main functions. It controls the flow of bioinks, and it also enables precise motion control to pattern these bioinks. But really, the microfluidic print heads are at the heart of the technology. So bioinks flow from the reservoirs into the print head. We can print as many as 4 different bioinks with a single print head. The bioinks, as I mentioned, can contain both cells and biomaterials, the biomaterials most often being hydrogel precursors, such as alginates. A material that can cross-link these hydrogel precursors into hydrogels is also flowed into the print head. So in the case of alginate printing, that would be a calcium chloride-based material. And the microfluidic print head then directs these materials so that the cross-linker fully surrounds the bioink, focusing it into a fine stream and then cross-linking it into a hydrogel fiber. These fibers that are formed in the nozzle can then be printed into a 3D structure. Now, the flow of these materials is controlled by valves that allow for rapid switching between materials, as well as the ability to create specific fiber microarchitectures. So in this demo, we'll be focusing on a print head that can be used to create core shell fibers. That's the Centra print head, but other types of print heads are available, and we are continuously developing new types of print heads. The Centra print head, as shown here, can print a core material surrounded by a shell material, and these are both then surrounded by the crosslinker sheath, thus creating a core shell fiber. And you can also switch between one of 2 different shell materials and one of 2 different core materials. So this microfluidic approach to bioprinting is quite cell-friendly. A common concern when researchers begin bioprinting is that the cells will be damaged in the printing process. The cells being printed here never actually contact the nozzle during extrusion, which differs from other nozzle-based dispensing approaches where shear stress during extrusion can damage the cells. And this is quite important for preserving the viability, phenotype, and function of sensitive cells. Microfluidic 3D bioprinting can also be used to print soft materials. So another common challenge in bioprinting is to print cells into structures with similar stiffness to in vivo tissues, many which are soft. But because the bioinks are cross-linked within the print head before printing, these softer materials with low concentrations can be printed with fairly high fidelity. So as I mentioned, we can print core shell fibers with the Centra printhead, and this includes both hollow and solid core shell structures. So hollow core fibers can be printed with cells directly embedded in the shell to mimic tubules. In this case, a viscous liquid is used as the core material and washes away post-printing. But because the cells are actually embedded in the shell, you can print hollow cell line tubules without the need for cell seeding. You can also print solid core fibers by using cells in the core or in both the core and shell, thus creating well-defined cell and biomaterial layers and interfaces. So using the Centra, variety of diameters can be achieved with a single printhead. And you can have independent control of the shell and the core dimensions. So, we can print fibers ranging from 1400 microns all the way down to quite small fibers below 200 microns. Here we have one imaged with a 130 micron outer diameter and a 40 micron lumen. And this ability to print these smaller structures can be useful when aiming to recapitulate some smaller biological structures, such as microvessels or the renal proximal tubule, for example, which is in the sub 100 micron range. Okay. So with a single printhead, you can change the diameter of a fiber in real time by varying the flow rates of either the biomaterial or the crosslinker. Here we show a fiber printed with a 5-fold range of fiber diameters, ranging all the way from about 750 microns down to 150 microns. And this is a beneficial capability when you're looking to, say, model different tube sizes in one structure or different curvatures. So core shell structures can be used to add an additional level of complexity to 3D tissue constructs. There are a variety of tubular tissue structures found throughout the body and its organ systems. And so recreating the shape is required in order to mimic certain functions, such as perfusion and flow or curvature, which can affect cell phenotype and function. And core shell structures can also be used to recapitulate the layers and heterogeneity of certain features in the body, such as the layers of blood vessels or the complex heterogeneity of tumor microenvironments. So just as an example of how core shell structures can be used to recapitulate the heterogeneity of tissue, we have an example here of some work where the Centra printhead was used to pattern cells into different regions, with some in the core and some in the shell. And so structures such as this can be used to model a variety of different types of biological interfaces. Okay. I've already mentioned the importance of printing soft materials. Most tissues in the body are fairly soft materials, consisting of cells within a tissue-specific ECM that influences cell function through both biochemical and biomechanical means. And so one approach to creating bioprinted tissue constructs is to take kind of a biomimicry approach. And to print cells into an environment that mimics the native tissue microenvironment of those cells. And that includes mimicking the stiffness of the extracellular matrix of the tissue, which can be challenging when trying to bioprint soft tissue constructs. So when attempting to bioprint these soft materials, researchers often find that there's a trade-off between high shape fidelity and low biomaterial stiffness. So when you look at common cell culture substrates, they're often these soft hydrogels that spread and coat the bottom of a plate and that allow many types of cells to thrive. But on the other hand, the materials that lead to the highest shape fidelity when 3D printed are most often stiffer materials that hold their shape. So in trying to balance these two in many ways opposing needs, conventional bioprinting often uses higher concentration hydrogels and polymers with shear thinning characteristics to obtain sufficient shape fidelity without causing too much harm to the cells. Now, in the case of microfluidic 3D bioprinting, the fact that hydrogels are cross-linked within the print head before printing means that softer materials can be printed with higher print fidelity. And so it provides just some more room for tuning the biomaterial stiffness. And this also means that multi-component bioinks can easily be prepared. So a low concentration of a quickly cross-linking material is used as the carrier, alginate, for example, and other cell supportive materials can be added, such as collagen, laminin, matrigel, fibronectin. And so the immediately formed network will maintain the shape of the structure, allowing the other materials more time to cross-link. So while these are helpful characteristics for printing soft materials are soft and won't always hold their shape post-printing. And in these cases, some good strategies involve patterning support structures. So the ability to rapidly switch between soft and hard materials is useful from an ease of use perspective and also provides some unique capabilities. Often the pattern support structures are acellular, which allows for more versatility in material selection and handling. And there are a number of ways that this can be done. So by printing acellular frames or handles for the printed structure, and we'll show you kind of an example of this in the demo. And then you can also provide support at the fiber level by encapsulating soft materials in a stiff shell. And that depending on the application, these supports can remain a part of your model or they can be removed afterwards. In the case of alginate, that would be by using, say, alginate lyase. Okay. Whoops. So here we have an example of printing soft or slowly cross-linking materials by encapsulating them in a stiff shell material. So we have a stiff alginate shell and collagen, just a pure collagen core. And this can also be useful in cases where cells printed in soft material and over time will produce their own ECM. Post-printing, you have the possibility of removing the shell using something like alginate lyase. Okay. So referring back to that earlier slide showing the center print head, I mentioned that it has the capability to print two different shell materials and two different core materials. So we see that schematic here. This capability means that you can print fibers like the one shown here, combining hard and soft materials or cell-laden and acellular materials. So in the top image, we see a hollow fiber printed from two different materials, where the blue is a stiff alginate and the pink is a lower concentration soft alginate. And the image below that shows a core shell fiber with the core switching from a cell-containing material to a cell-free one. And here is one example of how material switching can be useful. So it's challenging to connect a perfusion system to a hollow core fiber made of a softer material. And also you want to often reduce the amount of material, the number of cells that you're using. So if you can create these cellular ends, it will allow you to use fewer cells. So here, a hollow fiber made from these two different shell materials was printed, a stiff cell-free shell and a soft, potentially cell-laden shell. And the acellular ends can be made from a material selected specifically for connection to the perfusion system, while another material can be selected for optimal cell function. And so here we just see it being perfused with a red dye. I'll pass it on to Kyle now to give you a demonstration of the bioprinter.
Okay, thanks, Aaron. Yeah, hopefully everybody can see me here in front of the printer. And yeah, so up on the slide right now is this perfusible 3D tissue construct that we're going to be printing today. And so kind of combining some of the things that Aaron has already talked about is what we'll be highlighting with the center print head. So looking at the structure, essentially what we'll be doing is printing this multi-material 3D structure. Kind of shown in this light red or pink is a low percentage alginate that we'll use sort of as a scaffold to build up a couple layers of that, such that above that we'll be printing two different hollow core fibers. So in the actual slide, there is a blue one and a hot pink hollow core fiber. So we're going to print them both side by side. So we're going to switch from the low percentage alginate to a high percentage alginate to print those hollow core fibers, and there'll be a template material in the core there, which will help make it hollow. So once we've printed these two hollow core fibers over those first couple layers, we'll then switch back to the low percentage alginate, which is again shown in pink, to kind of finish off this three-dimensional tissue construct that we'll be showing today. So yeah, we'll go ahead and kind of do an overview of the system and get to printing now. So yeah, you're looking at the RX1 bioprinter, and essentially there's two main components to it. Sort of in the front here, we have our motion control system, so for full control of X, Y, and Z. And then in the back of the machine is our pressure system, which is what we use to flow our different bioinks and materials. So those are the two main components of the printer itself. And then, like Aaron was discussing at the beginning here, what makes sort of this microfluidic 3D printing technology unique are the print heads, which are the heart of the bioprinter. And I'll switch camera views here so that you can appreciate what those look like. So apologies with the camera work here. So we're now viewing the front of the printer, and we're looking at one of the central print heads. And we've got several different inputs, but really two main types. We have our material inputs, which are shown in the front here. So this is the Teflon tubing that is inserted into the print head, and those are connected to our materials. So we have our buffer and crosslinker here on the system, and then up here we have our bioinks that are housed. And so as you can see behind them, this is the pneumatic tubing. So this is what's used to pressurize these containers to get the materials to flow through the inputs, which then enter the print head. So the first input is a material input, and then in the back of the print head are these metal valve inputs. So these are what control whether or not the material is flowing through the print head. So these valves exist either in an open or closed state. So they're what's controlling which bioink is flowing and when. Okay, so that is sort of the print head mounted on the printer. The last thing I wanted to point out here is that we print directly onto a vacuum surface. So in this case, this is a square vacuum chuck with nylon mesh on it that we can print directly onto. And the purpose of this is to drain away the excess crosslinker, especially when you're trying to build up three-dimensional structures. It's important to drain away that crosslinker so that you're not printing directly into a pool of liquid. So this is a flat surface here. We can also, I'll switch over, we can print into the cell culture inserts. So these are just standard cell culture inserts that you can print directly into. And again, fitting into this special vacuum chuck allows you to drain away that crosslinker to build up a 3D tissue structure. Okay, so yeah, those are the main components of the RX1 bioprinter and looking at the print head. And so now we will jump into the software. Okay, so hopefully folks can see, I'm adjusting the size here. Hopefully on the left, you can see the screen share of the software. And on the right is a video of the print surface. So we'll be looking at that here in a moment. But jumping into the software now, essentially, this is Aspect Studio, which is our software that was designed specifically for the RX1 bioprinter. And so you can use the software for everything from designing to printing. And the way the software is organized is in these 4 different tabs that we start on the left side here in our STL editor tab, and then we'll basically progress us from left to right as we design our structure, how we want to divide it up into printable layers, and then ultimately what are the settings that we want to use to print it. So the software kind of guides us from left to right in that way. So starting in the STL editor tab, right now, we've created a sort of a rectangle, actually a square, structure here that we're going to use to print like a mesh-like structure. You can also create a few other shapes in Aspect Studio, but what you can also do is import STL files from other sources. So if you've designed something in another software, you can import that file here. The next tab in the software is Tissue Designer. And so now this is showing our 3-dimensional structure on the actual print surface. And what Tissue Designer is used to do is essentially divide this bulk 3D shape into printable layers. So you can designate, how many layers you actually want to use, which materials will be used, and you can really customize the design that way. So once you've established that, the next tab in the software is Toolpath Editor. And so now we're looking at that same bulk 3D shape that we've divided into printable layers. And so if I can sort of highlight this in a little bit more detail. So I will scroll back through the layers. So essentially what we've started here is the first layer we've printed with one material, just shown in blue here. And then if we kind of build up and sort of watch this print occur, we're sort of using this rectilinear infill to print each layer. So we're now alternating between the blue, the red, and back to the blue. And so in this way, with this particular mesh structure, we can build this up many, many layers and ultimately end up with this 3-dimensional structure with a pretty high density infill here. Okay, so this is sort of designing a 3-dimensional mesh structure. And one thing to point out is, using this fairly simple shape to begin with and using 2 materials, that there is a way to further customize this. So in the software, we can open up what's called Script Editor. And this allows you to really tailor and customize the design from everything from which materials are used to XYZ control, pressure control. You can do gradients, so you can change the diameters of fibers in real time during the print, and you can code that all here. So this is pretty handy to sort of take your bulk 3D shapes and really customize how you want to print them. So that's a really handy tool. Okay, so the last tab in the software is Printer Controller, and I'll explain that in a little bit more detail once the print has started. So I'm going to try and resize your view here. Hopefully the software is still on the left and about half the window size, and the print surface is on the right. So one of the first things that we'll do before actual printing is to wet the vacuum chuck. So this just helps create a seal so that we can get nice vacuum for aspirating that excess crosslinker. Okay. And so we already have our design loaded. So we're now gonna just home the printer. So it's moving the center print head to the center of the vacuum chuck. And I'm just gonna go ahead and hit print. Okay, so this is going to take a few minutes to print, and so I'm going to talk a little bit through what's in the software, and then we'll watch a material switching event in real time. So in the software, in the main part here, we have this central panel which highlights the different channels. So the 2 different shell materials, 2 different core materials, the buffer and crosslinker, and this is where you can designate their pressure. So really how thick of what the diameter of these fibers is. You can control all of that in here with pressures, and which influence the flow rate. So here, what we're printing with today is over off to the right here with the labels. Just to the right of that in the software this is the print head schematic. So this is just highlighting where those material inputs went into the print head, and again showing that with the Centro we have this sort of core shell architecture, which is corresponding to the core A and shell A colors here. The last thing I want to point out before we look at the material switching is over on the far left side, you can control the X, Y, Z motion with these various buttons. So if you're needing to reposition things, you're able to do that. So I'm going to switch to a print head camera view on the left now. So right now we're seeing the light red lower percentage alginate being printed. And so you're about to see it switch to dark blue. So this is the higher percentage alginate that also is using a template material in the core. So this is actually a hollow core fiber that's being printed directly across those first two layers of the lower percentage alginate. And then just again, we switch to the hot pink higher percentage alginate. So we're printing a second hollow core fiber right next to the blue one. And then it's going to switch back to the original red alginate to print these final two layers. So hopefully you're able to see those different material switching events. And so again, with our technology, essentially all of those inputs were connected to the print head, and then it was just opening and closing the different valves. So the switching was rapid, and you were able to see at least, basically 4 different materials kind of be printed there. Because with the hollow core fibers, it was a shell material, which was an alginate, and then in the core was a template material that's just a viscous liquid to help it maintain its shape during printing. Okay, so looking back in the software now, I'm going to actually pull up, this is the sort of design file for what we're printing today. So again, just kind of highlighting, sort of taking this bulk 3D shape and printing this mesh structure in the middle, and then using that script editor tool I was mentioning, we were able to sort of further customize this and print, if you're able to see it, sort of this blue line here and this red line down here, which were those hollow core fibers. So we were able to sort of customize this design to get this final structure, which is being printed right now on the print surface view. Okay.
Kyle,
yep.
Sorry to interrupt. We had one question coming in about the software, and so I thought maybe you wanted to take that one now.
Sure. I didn't. Let me see if I can find it.
I can. So the question is, for customization, is modifying the code the only way, or can we do that in the design space of the software? So while full customization, you can do anything really in the script editor. But if you pull open Tissue Designer, Kyle, you can still do layer by layer designs in the software, so fairly easily. We'll have.
Okay, sorry, Aaron. Tissue Designer?
Yeah, in the infill editor. So here, Kyle can add a layer. And so this is where he can choose a specific type of infill, so how each layer is patterned, choose different materials for each layer. So you can do a certain level of customization just within here, and then for really kind of fine detail sorts of customization, that's where you can get into the script editor.
Yeah, that's a great question, and just to kind of show what that would actually look like right now, since we have a couple of these pulled up, for those hollow core fibers that we were wanting to print, it's essentially sort of checking off that we're wanting to use open up the shell A valve, and then maybe for a core A material, so that would be that core shell fiber printing, and then you could do the same thing for another one. So in a second layer could be customized that way, and then obviously you can kind of keep adding them depending on what those actual materials are. And you have full control over, for each of those layers, what's the infill percentage, so how dense of the fiber printing will occur, and things like that. So yeah, thanks for bringing that up, and great question. Okay, so hopefully you all can see the print surface view, and I'm just going to grab the nylon mesh here and pull up this structure. So yeah, what we have is essentially a kind of solid support structure in the middle, which is that mesh in reddish orange, and then hopefully you can kind of see, maybe that's a better angle there, the blue and hot pink fibers that cross that tissue patch. So the reason we created this design was to have a support structure for these hollow core fibers that could then be perfused. So this is just showing the same printed structure that we did under the microscope. So this is a low magnification objective showing these adjacent hollow core fibers, so one in blue and one in hot pink. And again, showing the underlying fibers of the mesh structure, which is really a support structure. So hopefully you can appreciate when this movie loops again, that you'll see the two hollow core fibers on the left. And we just cut off the ends so that we could connect them to a perfusion system. So that's what you were seeing there. Next slide. So talking about these hollow core fibers and using them for perfusion on the same construct, we were able to embed fluorescent microbeads in the shell material, and then connect it to a syringe that was filled with these green fluorescent beads that were in the core. So yeah, the hollow core, we're able to flow in these beads. And if you go to the next animation, this is just a recording of these beads flowing through the hollow core. So it'll just loop back again. But you can see that these hollow core fibers are perfusible. And this is what we're observing here, is just flowing these fluorescent beads through the core and using the sort of stiffer alginate shell to support the fibers. Okay, so yeah, to sum up, sort of creating these complex 3D structures, we talked about self-friendly printing conditions. So the idea of minimizing shear stress during the printing process and that part of it. And talked about hollow core fibers, how to print those with our unique Centra print heads. And we were able to show that during the demonstration as well. Aaron talked about sort of the ability to print soft tissue constructs. So these hard to print materials, that how we're able to do that with the microfluidic 3D bioprinting technology, which is great for cells that often prefer soft material. So showed how to do that. And yeah, sort of the last idea here, and kind of with this, the micrograph that's shown on the slide, is this idea of layers and interfaces. So with this core shell architecture, you can have these, a core compartment and a shell compartment. You can have different cells in each, or one can be an acellular compartment and the other compartment can have your cell type of interest. So the idea of creating these layers and interfaces to recapitulate different structures, something we're really excited about. And yeah, this picture that's shown here was taken of 3 different cell types that were printed using the Centra print head.
Thanks, Kyle, for the demo. Yeah, so if you're interested in accessing our technology, or if you just have any other questions about it, feel free to get in touch. Again, I'm Erin, my email address is here, but we're more than happy to answer some of your questions now. So I'll stop sharing and let's take a look. So another question we got actually about the software was what software is Aspect Studio compatible in terms of importing STL files from other software. And the answer is any type of software that can create STL files. So if you are a pro with, say, SolidWorks and advanced kinds of 3D systems, those will work. If you're not, if you don't know what I'm talking about when I say SolidWorks, my personal favorite program is called Tinkercad. It's free, it's online, and you can create a variety of 3D shapes in that and just export them as STL files and load them into your software.
Looks like we've got another question about printing with cell densities. So what kind of cell densities can you print with? That's a great question. So we have printed with a pretty big range of cell densities, and obviously it would depend very much on your cell type of interest, sort of what density they prefer to be printed at. But we've printed as low as about 1 million cells per milliliter. And then in some cases up to about 200 million cells per milliliter. So pretty big range, but there are very different cell types. And so you obviously have a pretty big range there to print different cell densities to get the cells to be in a resulting structure that hopefully will recapitulate the biology you're aiming for. So yeah, 1 to 200 million is sort of what we've done, but pretty big range of cell densities that you can print with the printer. Yeah, good question.
Okay, thanks. So we have another question just related to some of the printable diameters and maximum and minimum sizes. So there's, in terms of the fibers themselves, we can print fibers ranging from, so hollow fibers, as low as 150 micron outer diameter with a smaller lumen. For solid fibers, we can go as low as 50 microns. And all of that is quite biomaterial dependent. So actually we do have examples of, for certain materials like silk, using different types of cross-linking, you can print down to 5 or 10 microns. In terms of maximum fiber diameters, I showed the about close to 1500 microns outer diameter with the smaller core. And then in terms of maximum sizes of structures overall, so that is mostly just limited by the size of the vacuum chuck. So it's that vacuum chuck is the print surface on the front of the printer there. And so, you can print to the edges of that when you need a vacuum flow. The printer itself can move further, but it's so you could, in theory, have a different vacuum chuck, but that covers more area. Okay. So kind of on that note, we have a question about with taller structures, does the vacuum have an issue removing the crosslinker? So as you tend to build up the structure, it's true that that suction has to be stronger in order to reach the top part. What we find is you can build quite tall structures and you'll still have that vacuum flow as long as there's some porosity still in your design. But that's a really good question. And there's some strategies you can use there to build some holes into your design to keep having that flow. Okay.
So I'm seeing another question kind of asking about perfusing core shell fibers, and I believe is referring to the slide in the presentation of using 2 different materials, sort of having these stiff acellular ends to be able to connect to a perfusion system, and then sort of a softer material that you'd have your cells printed in. And the question's really getting at about material adhesion at the interface of those kind of the softer and stiff material, and then asking if use any type of glue to ensure the tight adhesion. So good question, sort of thinking about the the practicalities of those perfusion systems. So to answer the first question, it depends on what materials you're using. So the way the transition works is you could have it be sort of an abrupt transition where you go from your stiff acellular material directly to your softer cell containing material, or you could sort of create a gradient. So it really depends on which materials you're using, and sort of to get a nice transition between those two. So you have some wiggle room to sort of design what you want there. And then the second part of that question is we do often use like gelatin to sort of seal the connection of where we've inserted the syringe needle into these hollow core fibers, just to create a nice seal, so that when you start applying pressure to flow your material in the core channel, that just helps ensure a nice connection that way. So yeah, someone's been thinking about perfusion. Great question.
Okay, so thank you all so much for joining us. We hope you're enjoying SFB, enjoying the conference. I've been hearing some great talks. Thank you for the great research you've been presenting here. It's been a pleasure. And yeah, don't hesitate to reach out if you have any more questions. Kyle and I would be happy to answer. And enjoy the rest of your week.
Yeah, many thanks for joining us, everyone.